Well, so here we have the partition-based algorithm, that is your quicksort, which works with respect to your divide and conquer technique, where the quicksort works in such a way that it assumes the first element as a pivot element. It assumes the first element as a pivot element. The working of your quicksort is simple in such a way that you search a position for your pivot element. You search a position for your pivot element in such a way that the elements towards the element towards the left of the pivot element is lesser, where the elements towards the right of your pivot element will be greater. So that is how we search. And here the input array what I have taken, this is for the worst case efficiency of your quicksort. Actually, if it is like, assuming that you have taken the one itself as your pivot, and that is exactly the pivot position, but it may not, it divides the array into unequal parts. So this makes algorithms to this makes the algorithm to be difficult, right? So here, so what is that we have is we have, yeah, I just said about the time complexity of your quicksort, right? In case of the time complexity, what exactly we have is T of n is equal to T of n by 2 plus T of n by 2 plus n. So what exactly it is? This is to divide the left part of array. This is to check for the right part of the array. The same way here, this n stands for to find the partitioned element, to find the position of the partition element, because it has to go for all the n elements, right? So that's why T of n is equal to twice of T of n by 2 plus n. And obviously, to find, in fact, we can do this by using backward substitution method. The time complexity of your algorithm, right? The time complexity of your algorithm can be, especially time complexity of any algorithm can be found out by using backward substitution method, right? But if you backward substitution method, right? And here we can actually, for the recursive algorithms, we can actually use for master's theorem. Okay, we can use the master's theorem. Observe, in the master's theorem, what it happens, we have an equation, that is T of n is equal to a of T of n by b plus f of n, right? Where you have to check for the values of a. What is for the a I have here? Okay, let me just write a master's theorem general form so that you'll understand it better. So here I have it as T of n is equal to, no, T of n is equal to, I have theta of n par d whenever your a is greater than b par d. You just replace the value directly with theta of n par d whenever your a value is greater than b par d. The same way, whenever your a is equal to b par d, so what you will do is you just replace into n par d into log n to the base b, right? And next, whenever your something is missing, I think this is supposed to be lesser. I think this is supposed to be lesser, right? So whenever your a is greater than b par d, it is theta of n to the power of log a to the base b, right? N to the power of log a to the base b. Alright. We'll just let's confirm this. What exactly that equation is. Very well, just 1 second. I think this is correct, but let me just check it out. Well, so that is the thing is, yeah, it's correct. Like, whenever we have for the master's theorem, whenever your A is less than B par D, the first one is correct, whatever we have this taken. Right. So now you observe carefully here. What is when you compare this equation with this one, you just tell that A consists of two, and in fact B is also two. But now you simply feel like, sir, where is exactly D is? I'm unable to find it. Observe, as they have said that whatever you have, it is a function of f of n. In fact, your D is exponent of your n, right? D is exponent of n. If nothing is there here, we assume it as 1 here. Sometimes, you know what, we'll be having only like this, T of n is equal to, maybe probably I have only T of n by 2 plus 1, like, not plus n, sorry. Sometimes I have 1 here. How 1 can be written? How 1 can be written? I can just have 1 as n power 0, right? I can just write it as n power 0. By this time, it is D is equal to 0, right? So in fact, you know what? This is your, this is your, equation for your binary search. In fact, only for the understanding purpose, I have taken. Anyhow, it is actually the binary search equation. It is the recursive equation. I'll show that one also after doing this. Observe then what is the value of D we have right now? It is 1. When I just equate it, it is 2 power 2 is equal to, sorry, 2 is equal to 2 power 1, it is equal to 2 is equal to 2. Hence, the time complexity of quicksort will be the third case, right? It is theta of n power 1 into log n to the base 2, right? Because b value is 2, right? So that's why I have got t of n is equal to theta of n log n to the base 2. This is for your quicksort. Okay, guys, the same thing applies for your merge sort. Observe, let me take your merge sort first. What is that merge sort happens? The same thing, but here you divide the array in such a way that, you divide the array in such a way that further division is not possible. You have like this, you keep on dividing. Maybe in one side you get 3 elements, in one side you get 2 elements, and what exactly you do here, maybe properly this side you get 1 element, and here get 1 element, and here already you have what, 1 element, right? Further the right side will not be divided again, so now you get 1 element here, right? Observe carefully, guys, this is how it happens, right? This is how it happens. Now observe, what I'll do is, while I'm conquering, I'll just conquer in such a way that it is been sorted. All right, it has been sorted. That's why we need an extra array here, because when I compare that, that is supposed to be stored somewhere else, right? If it is bigger than if it is lesser, so like that we'll just consider, right? So this is how exactly it happens, and at the end I'll just merge this array, right? I'll just merge this array, right? This is how your merge sort works. Observe, guys, I'll come to your algorithm, you need not worry, I'll come to your algorithm. I'm just telling the logic how your merge sort works. Observe, as in case here also we have seen that t of n will be equal to t of n by 2 plus t of n by 2 plus n. What is this t of n by 2 is? This is to divide the left part of array, and this is to divide the right part of array. But here this n stands for dividing an n elements in an array. Observe carefully, guys. The same recursive equation when it was in your quicksort, I explained for some, I explained that n was supposed to be to calculate the mid element, sorry, to calculate your partition, like a pivot's position, right? It means that to divide the, to check for the element position, like the pivot's position, right? And here I have only one. Whenever I have only one element, surely you may understand now. For example, twice of t of n by 2 plus n, right? Now observe, I don't solve this using a recursion, master's theorem right now. What I'll do is, by this time I'll solve this using backward substitution method. Observe carefully, guys. Now I'm solving this method using backward substitution. Now if I want to go for the backward substitution method, what I have to do is, if I want to get the solution, then I have to know the value of this particular t of n. So sorry, t of n by 2. What is t of n by 2 for me? Observe, when the problem was n, it was supposed to be twice of t of n by 2 plus n. Then what will be t of n by 2 is, it is twice of t of n by 2. Just replace your n with n by 2. Okay, this is how you get. Right now, what exactly? I'll not multiply. Just keep it in mind. I'll not simplify it. I'll not just simplify it. Observe carefully. I'll just take it as 2 square. Right? This is n by 2. Clear? Now I'll substitute this. I'll substitute this. It becomes, already 2 is outside. So twice of t of n by 2 square plus n by 2 I have. When I multiply 2 inside, it becomes 2 square t of n by 2 square plus 2 and 2 get cancels. I have left out with n. I forgot there was one more n here. Right, because we have substituted for this, right? There was one more n here. So now I got for the value. So I got this. So I can just simplify. Yes, of course, I could have been done here only. Let me just take like this. It is t of n by 2 square plus 2n. Right now, I have to check for this t. In fact, I can write it as n by 4. Not an issue. Right. For the simplification, further I'll just shift that. So for that's why I have just kept like as it is. Now I have for t of n by 2 square. Now I have to replace my n with n by 2 square, or else you can just take like this, n by 2 with n by 2, right? So twice of t of n is replaced with n by 2. Already 2 square was there before only. So now this became like this, right? Now observe carefully. What is that it happened right now? It became 2 into n by 2 to the power of 4 plus n by 2 square. Is that become power or 3? It's 3, right? So now why, sir, if we got 3 here, why we are getting 2 square? Because we have only n by 2 outside, right? Now let me just substitute this value. Let 2 square be outside. I have twice of t of n by 2 cube plus I have n by 2 square. The outside I have 2n, right? And now when I simplify this, observe, when I simplify this, I'll get 2 cube t of n by 2 cube plus when I multiply this 2 and this 2 get cancels. I have remained with n plus 2n. So I have remained with 2 cube t of n by 2 cube plus 3n, right? Observe, guys, when I simply keep on doing here, surely I can do for the another steps also. But now I can take for the n values because already n is available, then I have to take for the other one. Now it is supposed to be 2 power I. You can take any values. 2 power I into t of n by 2 power I plus I into n. Right? Can I do like this? Can I just take like this? Surely I can take.
Yes.
Now I have to substitute in such a way that this this term will become, and this term will become, yeah, this term will become 1, right? How I can do this? In fact, when I just take this 2 power I t of, like t of 2 power I divided by 2 power I plus I into n, such a way that now, of course, I would have been taken this as n. Let it be like that only. We'll just come to know that. Okay, your equation was supposed to be like this. It is twice of t of n by 2 plus n, right? Twice of t of n by 2 plus n. So this was greater than 0. It was supposed to be 0. Okay, it was supposed to be 0 for when n equal to 1. Because when you have one element, you need not sort anything, right? Yes, of course, it was supposed to be 0. So now what it happens? Yeah, 2 power I into 0 plus I have I into n. right? Plus I have I into n. So what is that I have remained with? I have T of n is equal to I into n. Now actually what I have assumed here is I just assume that I'm substituting n value as 2 per I, right? I'm substituting n value as 2 per I. Now actually I have to express this terms in 2 per I itself, right? Now I have to express this in 2 per I itself. So means it has to be in n terms, right? So what is that? It happens is how do I get that? How do I get that? So apply when I want to make this term as one. Something is missing. I'll just check. Something is missing here. So log n to the base 2. So I have log 2 to the base 2 to the power of I. In how does it would look like? It would look like log of m to the power of n. How I can write this? N into log of m I can write. And let me just write it is log n to the base 2 I into log 2 to the base 2. And also like log 2 to the base 2 is nothing but 1, right? That I have here. So I get I value as log n to the base 2, right? Then I'll substitute this value. It becomes P of n is equal to, I'm substituting for I already have n there. It becomes log n to the base 2, right? This is what it is. This is, I'm expressing this in terms of theta. I can also express this in the other ways also, right? Because we have to sort all the elements, right? So hence the time complexity of your quick sort and merge sort is supposed to be same in case of omega and in case of theta. Why is it so? Because even your even your merge sort takes the same time because both takes same design technique. But only drawback of your quick sort is it takes, in a worst case, it takes n square. Other than that, the rest all is same, right? But still, the working is different, right? But still, the working is different, right? And what else we have? So this is what with respect to this, and the divide and conquer. In fact, in the divide and conquer, we come up with Strassen's matrix multiplication of large numbers, and defective chessboard problem we have. Yes, we can take in that fashion also, but still I'll just consider your binary search. Observe, I'll just take your binary search, guys. What is that? In a binary search it happens, you all guys know about this. Like you have you have a array here, and of course that is sorted, right? And of course you have, it is a sorted array you have, but it is 10, 20, 30, 40, 50, 60 you have. I'll take this as low and I'll just take this high. Now what I'll do is I'll simply calculate the mid element. I'll just simply calculate the mid element. It is low plus high by 2, right? What is that low I have? It is 0, 1, 2, 3, 4, and 5. So it is 0 plus 5 divided by 2, it is 2.5. The integer division is 2. Right? Now this is a mid position for me, right? Now this is a mid position for me. The same way, what is that it happens here is, observe carefully, you check for the conditions. Assume that the case 1, assume that the case 1, if if the a of mid equal to key. If this is the case, what you do is you simply return the mid value, right? You simply return the mid value. The same way, the same way, else if, right? Else if your key is less than a of mid, right? If your key is less than a of mid, you call for the binary search again, where you are giving a comma low comma mid minus 1. You are searching only in the left part of array, right? Or else you are searching in the right part of the array. This is left part and this is right part. So it is nothing but mid plus 1 research, and this algorithm where it takes a comma low comma high. Let me just close this, right? And it keeps on dividing until it gets a mid element. This is how you work with the recursive concept of your binary search. Now observe, how do I write a recursive statement, recursive relation. Observe guys, when you are finding a time complexity for your recursion algorithm, this is most important thing. You should be knowing like how to write the recursion relation. Observe, once I search for whenever I have n is equal to 1, I search for one thing, that is 1 unit of time, that is 1. So whenever it is for n is equal to 0, observe carefully. For time complexity, observe for this thing, I'm taking t of n is equal to twice of t of n by 2, right? Twice of t of n by 2 plus 1. Now assume I'll just do it for the master's theorem, right? I'm just doing this for the using master's theorem. Okay. In this, what I'll do is I'll simply take my general equation. It is t of n is equal to a into t of n by b plus f of n, for showing you that where exactly d remains. So for that reason, I'm taking. Now when you equate this for the relations of your master's theorem, is it is theta of n power d when your a is less than b power d, theta of n power d into log n to the base b when your a equal to b power d, and theta of n to the power of log a to the base b when your a is greater than b power d. Now just equate the relations, equate the constants here. So what is that you have for A? It is equal to 1, right? And B, you have it as 2. Now, in fact, you are unable to find the function, right? You are unable to find the function of f of n. So what you can do is you can just simply write your n1 into n power 0, right? Now, D is nothing but 0. Now just relate this. It is nothing but 1 equal to 2 power 0, which in turn 1 equal to 1. Again, it holds good for your second equation. So it is t of n is equal to 1, right? 1 into t of n power 0 into log n to the base 2, right? So I get it as t of n is equal to t of n, sorry, n become 1, right? Sorry. So we get it as log n to the base 2, right? Log n to the base 2. Hence, a time complexity for or binary search is something like t of n is theta of log n to the base 2. Since it holds good for all the three cases, that is your uh, what is that, best, worst, and average case also, right? So because it always searches the mid element, right? It always searches the mid element. Either if your element is present or not. Either your element is present to the left extreme or to the right extreme. Whatever you take, that is the worst case of your, means worst, best, and average case of your binary search would be log n to the base 2 itself. Observe when you compare this thing with your linear search. Guys, when you compare this with your linear search, observe, I'll just take one example for your linear search here. What is that linear search tells? You have given an array for me. You have given an array for me which is unsorted, and I have an array. Then you have given a key for me. Imagine that I check for each of the element. I check each of the element, and for your best case, the element would be present in the first position itself, right? Whereas the average case can be either it can be the second position or it can be the first position itself. So whenever it is for your best case, position or n minus 1th position. Both can be the average for me. So of it, the worst case time complexity of my linear search as big O of something like this. In case of linear search, what I'll do is while I keep on repeating key means, then I keep on incrementing the value of a of just I. Right. After this, I return I. If any of it is not present, surely we return -1. Right? This is what exactly a linear search is. It's a bit simple. And observe for how many times it has to run. Like we usually run this, okay, and I can also have equation here itself. It has to run till when I is less than n, right? When I is less than n, I keep on incrementing the value of I have initialized my I value 0, right? And if this is the case, it returns a I. If not, the element is present, it returns a -1. Observe, whenever it's comparison, sometimes your basic operation can be inside the loop, or it can be the condition of your loop itself, right? It can be, of course, I can split this one also, not a problem. By that time, what we have to do is we have found out the basic operation is comparison. In fact, it takes 1 unit of time. For how many number of times it is repeating from 0 to n, right? It is from the non-recursive algorithm. Always to remove this, we have to construct this. Actually, we should only construct this to calculate the time complexity. What we do is we simply construct in such a way that so basically repeating. If this is first, then we have to remove this. This is upper limit minus lower limit plus 1. So what's the upper limit for me? It is n. What is lower limit? It is 0 plus 1, right? Observe, when we are calculating the time complexity for the n values, plus 1 is ignorable, right? Plus 1 is ignorable, so that big O of n, right? Now tell me, this is for your linear search, and I have this for in the worst case as log n for the binary search. So we prefer this, right? Look, like this. Maybe in your interview questions, you may get that they may give some, they may simply give the order of growth. Okay, they may ask you what the order of growth. Yesterday, I have just shown you, right? When I was explaining, I just said the one is less than log n and log n is less than n, and in fact it is n log n is less than n is less than n log n, and we have something like n square n real, right? It is just the equation. Knowing this, if you know this, surely we can tell that okay, the algorithms what they have given for you takes less time, right?